Why is diffusion more prominent at lower frequencies compared to charge transfer? How do the charge transfer process and the diffusion process interact to create this characteristic semicircle and slope line on the Nyquist curve? What is the significance of the slope line of diffusion impedance, and why does it typically have a specific angle, such as 45 degrees? What does it mean if the slope line deviates from 45 degrees, and what factors could cause this deviation? How does the surface characteristics of the electrode influence the diffusion impedance, and why might deviations occur due to changes in the electrode surface? What factors, such as surface roughness or non-idealities in the electrode material, could lead to a deviation from the expected 45-degree slope? How does this deviation affect the interpretation of the Nyquist plot, and what additional insights can be gained by analyzing these deviations in the context of electrode behavior? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does understanding the behavior of both charge transfer and diffusion processes as reflected in the Nyquist curve contribute to optimizing electrochemical systems like batteries and fuel cells? What happens when the electrode surface is so rough that the diffusion process becomes partially equivalent to spherical diffusion, and how does this roughness affect the electrochemical measurements? How does the roughness of the electrode surface influence the impedance measurements, and what does it mean for another state variable other than the electrode potential to cause impedance during measurement? Why is impedance best understood through equivalent circuit diagrams, and how do these diagrams help visualize the electrochemical processes taking place? How are equivalent circuits drawn by adapting a complex circuit? And why is it necessary to simplify the real-world circuit into a form that's easier to analyze? What is the concept of an electrochemical system as an equivalent circuit? And how does this analogy help in understanding the behavior of electrochemical systems? What basic components are typically included in an equivalent circuit, such as resistance, R, capacitance, C, and inductance, L? And how are these components combined in different ways, such as in series or parallel configurations? Why are these basic components essential for modeling electrochemical systems? And how do they represent the different aspects of the system's behavior? In an AC equivalent circuit, why is only the circuit associated with the AC signal considered, while the DC circuit is omitted? And what does the simplification allow for in the analysis? What is the role of the coupling capacitor in the original circuit, and why is it viewed as a path in the AC equivalent circuit? How does the coil in the original circuit behave as an open circuit in the AC equivalent circuit, and what does this mean for its role in the impedance measurement? 1.